All right, hi everyone. Welcome to sections 4.6. And in this section, we're going to be learning of a new method of solving a non-homogeneous differential equation, and that is the method of variation of parameters. Okay, so our main learning objective for this section is to define and apply the method of variation of parameters to solving non-homogeneous differential equations. Okay, so what we've seen previously so far in solving non-homogeneous differential equations came in section 4.4. Okay, we solved a non-homogeneous differential equation of this form. AY double prime plus BY prime plus CY equals FX, where f of x is some finite product or sum of the following four criteria. In these are constant coefficient differential equations. Okay, so this criteria and method causes a specific weakness with this method of constant coefficients. So what if we want to solve a non-homogeneous differential equation that doesn't fit this criteria? What if this f of x isn't a finite product or sum? What if we have constant coefficients, but this f of x doesn't fit our criteria for using the method of undetermined coefficients? So that's the main points of variation of parameters and how we can use this to solve the differential equation. So this variation of parameters method came from Joseph Lagrange. Okay, he's a famous mathematician and astronomer, and he produced a method for determining our desired particular solution that, in theory, has no restrictions on it. So that makes it great. That makes this possible for us to solve the differential equation. And this method is known as variation of parameters. Okay, so variation of parameters. Our goal is to solve any differential equation of this form. Okay, so this looks a bit familiar. The only thing is that this g of x, this is not a finite product or sum. Okay, so that's why we would have to use variation of parameters because it's not a finite product or sum that would throw our work with undetermined coefficients off. Okay, so we would need to, for variation of parameters, come back to something we know by putting this into standard form. What that means is get y double prime naked. Okay, so something we are a bit familiar with getting into standard form. And so when we get y double prime naked, that makes this f of x our what's called an input function. And we're going to use this input function to figure out our trial particular solution. So here's the steps for solving. It's same thing as undetermined coefficients. We want to solve for the complementary solution. Okay. And then we're going to get our two solutions, um, we'll get our two solutions, YC equals C1 Y1 plus C2 Y2. And then we want to get our differential equation to standard form. So what does that mean? That means get y double prime naked. And the third thing we're going to do is make a guess for our trial particular solution. And this right here, yp equals u1 times y1 plus u2 times y2. This will always be our guess. You don't have to come up with anything else. This will always, sorry, this will always be our guess. Okay, so when we're doing variation of parameters, our guess will always be u1 y1 plus u2 y2. And these are the formulas for u1 and u2. Okay, it's a negative integral of u2 times the input function f of x divided by our good friend, the Wronskian. Okay, so just recall the Wronskian of two functions is the determinant, like y1, y2, y1 prime, y2 prime. So then it's like y1 times y2 prime minus y2 times y1 prime. Okay, so just a little bit of recalling what Wronskian is. We need to determine that, and we have a formula for u2. Okay, so we have a lot of integrals to calculate. Typically, one integral is always easier than the other one. It's always quicker. One's always a bit longer, like integration by parts or something along those lines. But that's pretty much the setup for variation of parameters. We just have to get our u1, u2, or y1, y2, and that'll be our solution. Okay, so that's it for this video. We're setting the stage, and I'll see you in the examples. Okay, take care.